I don't know why my parents decided to do that to all the people who are introducing me. For whatever it's worth, my name is Aanjhan Ranganathan. Thank you for the introduction, and a very good afternoon to one and all present here. In the recent years, we have seen an increasing number of privacy and security critical information leaked through mediums that were originally not imagined to be used for data communication and exfiltration. One of the main challenges for an attacker, even after infiltrating into a secure system, is to extract or is to exfiltrate this sensitive data out of the system. In contrast to previous work presented, where the authors showed how to exfiltrate data out of an air-gapped system, in our work we focus on covert channels that exist within a platform and how relevant it is to modern-day computing. Let's take the example scenario in the cloud. Consider the scenario where you have two co-located virtual machines running on the same hardware platform. One virtual machine contains sensitive data. It could be credit card information, it could be authorization keys, it could be anything. And it has already been infected and infiltrated with malware. Now the challenge for the attacker is to exfiltrate this sensitive information out to a neighboring virtual machine, for example, which is located in the same hardware platform without being detected. One way to do this would be to use intended communication channels. For example, they can use networks, they can use inter-process communication techniques, you can use files transfers, but however, such techniques can be typically detected using information flow tracking and tainting methods that have been explored in the literature. Another way is to use covert channels. Covert channels basically means that you communicate through a channel that is not designed for any kind of information transfer. And these covert channels are pretty hard to detect. There are many ways to achieve covert communication. Let me give a couple of examples. The attacker, for example, could leverage the use of shared resources indirectly to communicate data. For example, the attacker, the source application, that is the application that is intending to transmit these sensitive data out, could raise an exception, which would potentially set a particular CPU register, which the sink can continuously monitor to decode the data. Another way is to use timing channels. Basically, the source application can voluntarily manipulate the time taken to accomplish a task. For example, the source can hold on to a CPU for X amount of time to communicate a 0 and Y amount of time to communicate a 1. The underlying common factor is the presence of shared resources. Yes, it's all about sharing. Hence, an obvious solution to share is to share as few resources as possible, if not any. Yeah, sharing is not caring in this option. So applications, for example, can be allocated dedicated resources such as CPU cores and memories. For example, the source application shown inside the green box has access only to cores 0 and cores 1 and not to the cores allotted to the sink, shown within the red box. An alternative way is temporal partitioning. Basically, in a temporal partitioning technique, the applications share the same resources, that is CPU and memory, however, in a time multiplex manner. This can be thought of to be very similar to modern-day Intel TXT or the ARM trust zone, where either the trusted world or the insecure world has access to the system's resources at any given point in time. These methods are widely believed to mitigate a majority of covert channels. What we show in our work is that despite temporal and spatial partitioning, how an attacker can leverage heat, a natural byproduct of any computation, to exfiltrate data out of the system, or rather within the system, out of the core. So in other words, we demonstrate the feasibility of thermal covert channels in multi-core systems, which are the workhorses of modern-day commodity desktops and commodity servers, despite temporal and spatial resource partitioning, and explore the factors that affect the throughput of such channels. In addition, we also show some preliminary results on how thermal data can be used to infer information on processes running on neighboring cores. That is, in other words, the possible existence of thermal side channels in such multicores in modern multicore systems. The key question we try to ask through our research is that, is there actually an upper bound or a limit to how much isolation one can achieve on modern multicore platforms? The primary requirement for constructing communication channels based on heat is the availability of thermal sensors on modern x86 systems. The figure shows the major components of a modern x86 system and the presence of thermal sensors indicated by those thermometers. You can find thermal sensors these days in memories, embedded into memories, processors, chipsets, hard disks, so on and so forth. Even more, in a multi-core processor system, actually Intel has each core in a multi-core processor system has a thermal sensor embedded into it. Additionally, there is a rising trend of thermally aware or energy efficient computing that requires user-level applications to have access to these thermal sensors. Initially, in the olden days, the thermal management was done completely in hardware. That is, as soon as the temperature of the system rises above a certain threshold, the protective circuitry kicked in and just simply turned off the power to prevent burn-off. Then this was followed by a hybrid software-hardware approach to dynamically modify the frequency and voltage of a CPU. Now, more recently, there is an increasing trend towards allowing the users to set thermal policies. In other words, the trend is that the thermal management is becoming more and more user-centric. For example, Linux actually allows the user to configure thermal policies. In this work, we focus on thermal sensors we leverage the thermal sensors that are available on each of the cores of a multi-core system. With this information, we proceed to examine the thermal behavior of cores when subjected to CPU-intensive operations. The figure there on the above shows basically an 8-core processor with linear arrangement of cores. And this arrangement can be found from data sheets or standard tools that are available. What we did was to execute a decryption algorithm. In our case, it was RSA, for about 100 seconds, while the remaining cores C0, C1, C2, and the ones shown in black basically idle. What we observed was the fact that as soon as the application started executing, there was a steep rise in the temperature, and then the temperature saturated at some point. Once the computation was stopped, there was an initial steep decline in temperature, but then after which there was very gradual decrease before the system reached the ambient temperature again. That is, even after several seconds after the application was stopped, there was still some remnant heat here. I'll come back to this in a couple of slides. Next, as we all know that heat is a physical quantity, it propagates. And we wanted to see how heat generated due to a core's computation affects the neighboring cores. So what we did was to run the application on core 3, in this case shown in green, and observe the temperature of the neighboring cores at one hop. That is, there are C2 and C4 shown in red and blue. What we observed was that there was a very strong correlation between the temperature traces of the core 3, where actually the app is running, and its neighboring cores. This implies our hypothesis that, yes, the neighboring cores are getting affected. We even took it a bit more further and wanted to observe the effect of core 3's computation even on cores that were 2 hops away. For example, as shown in figure, the application was running on core 3, and we observed the temperature on core 1 and core 5, which were basically 2 hops away from core 3. And still, we got a strong correlation. Given these observations regarding the thermal behavior of the cores, we now ask the question how an attacker can leverage or exploit this behavior to construct thermal channels. I would like to summarize the observation, and the first observation was that the computation on a core not only affected its core, but also the neighboring cores. So can an attacker actually leverage this behavior to overcome spatial partitioning techniques? What are its implications? And the other observation was that long after a computation was completed, there was still some remnant heat. What are the implications of temporal partitioning? Can an attacker leverage such a behavior and overcome temporal partitioning? So as a first step, we built an experimental framework that enabled us to find answers to these questions. Our hardware was basically a commodity Intel Xeon server, which consisted of 2 processors, with each processor having 8 cores. That is, basically, it was a 16-core commodity server. We restricted the operating system to processor 1 and ran the source and the sink on processor 2. This was done in order to limit the interference from the operating system and emulate the best-case scenario for the attacker. One could imagine the source and the sink here to be 2 virtual machines, basically. The source was the decryption algorithm, and the sink was simply a mechanism to read the thermal sensor of the core on which it was running. Our framework also allowed runtime configuration of the source and sink as to which core it has to run and for how much duration of time. With this setup, we will now see how we can construct a thermal covert channel in spatially partitioned system. That is, the source and the sink run on dedicated cores and execute concurrently. We simply chose to use on-off keying technique. That is, basically, if the source wants to communicate a 1, it executes the computation, and when it wants to communicate a 0, it simply remains idle. At the same time, the sink simply monitors its own core's temperature, and we ran it on a neighboring core, or will monitor its own core's temperature. If everything goes well, then as per our initial observations, we should observe whenever the core is performing some computation to transmit a 1, we should observe the fact that we should observe in core 2 a temperature rise, which the sink can demodulate and detect a 1 or 0 otherwise. An important question here is to figure out how long should the source run the computations in order to let the neighboring core heat up, and such that the sink can actually detect and demodulate the data. This depends on several factors, including sensor resolution, the frequency of CPU, and so on. We provide a thorough evaluation or exploration of these factors in the paper, and which I would not go into detail in my presentation. To validate this hypothesis, we ran our source and sink applications on our framework. Basically, we ran the source application on core 3 and the sink application on core 2. We obtained the following. So for people here who do systems research, after all this hypothesis and work, to see such a graph is bliss. I went out for a beer after this graph. What we found out was that it was sufficient for the application to be run for about 750 milliseconds, such that this affected the neighboring core's temperature sufficiently large that the sink was able to successfully decode the data. We sent 1,000 random bits and were able to communicate approximately with errors just over 10%. What this means is that with error correction, for example, it could be possible that the credit card information, such as credit card numbers, expiry dates, and the security code, can be transmitted in 4 minutes in a spatially partitioned system. Next, it's to determine how to construct a covert channel for temporally partitioned systems, where the source and the sink run on the same CPU, but however in a time multiplexed manner. I would like to restate the fact that here we will leverage the remnant heat, that is, the heat that remains even after a computation has been completely stopped. Similar to the previous scenario, the source transmits a 1 by performing some computation and a 0 by remaining idle. If everything works as per our initial observations again, we should see something like the graph shown below. When the source is executing its computation, it heats up its own core, And then by the time the next time slice happens, when the sink is executing, it should see a falling temperature, or it should not see any change in the temperature to detect a 1 or a 0 respectively. The same question holds here as to how long the source has to execute such that it leaves enough remnant heat for the sink to come in the next time slice and detect the data that it is trying to transmit. So when we run the source and the sink on the same core, we observe the following. The green lines are the temperature measurements of our sink application. Remember that they do not have access to the thermal sensor while the source is executing. Hence, we show the temperature change when the source is actually running its computation as a simple interpolation of data using the red dots. We observed that it was sufficient for the source to run its computation for about 10 milliseconds to increase the temperature to a level such that the sink that is executing in the next time slice was able to decode the data correctly. As before, we sent 1,000 bits and were able to decode with about 7% errors. What this means for the credit card example, it is that the credit card details can be transmitted in about 5 seconds. Given that heat is a physical quantity, can we at all prevent such a covert channel? The most obvious countermeasures are to separate the processes temporally and spatially. For example, in a temporally partitioned system, the source and the sink can be separated in time far enough. That is, we do not allow the sink to execute, we allow the sink to execute only after the remnant heat dies off completely. In the spatially partitioned systems, one could simply separate the processes far enough, say maybe 3 hops or 4 hops away, and not run anything on the intermediate cores. Of course, this results in wastage of resources. Another option could be to simply restrict the application access to thermal sensors. However, such information cannot always remain hidden. In today's many core architectures that are popping up everywhere, centralized cores on these architectures does not scale well. For example, Intel SEC allows each core to monitor and administer the frequency and voltage independently. For example, the software at each core should track probably the thermal information to schedule intelligently and to detect if any of its thread is misbehaving. Therefore, what we would like to point out from this work is that there is a tension between securing platforms and improving their energy efficiency by exposing this thermal data to software applications. So let's switch context a little bit from covert channels. With the humongous amount of data we collected, we became curious whether there can potentially be a thermal side channel. In other words, would it be possible for an attacker to infer certain information regarding the process or application that is executing on a neighboring core by simply observing its own core's thermal trace? We show some preliminary study in the paper where we were able to successfully distinguish between different algorithms and different applications, and also we were having a very high accuracy between distinguishing between applications that were CPU intensive and that were not CPU intensive. However, we were also getting a lot of false positives at some points in time. So the question is, will more advanced metrics, such as thermal models, which people are working on for modeling, such as modeling different cores, modeling different applications that are running on cores, and machine learning-based classifiers, result in more fine-grained data extraction? For example, would it be possible to extract secret keys, for example? However, there are several challenges here. For one, the allowable time resolution, or rather the refresh rate of these thermal sensors. Currently, you will be able to read out the values only once every 2 milliseconds. So you will not be having any granularity currently less than 2 milliseconds. Also, the sensor resolution. What we found from our experiments was that the sensor resolution was somewhere around plus or minus 1 degree Celsius. But this is bound to change with Intel pushing out the more and more advanced thermal sensors into their cores. And we hope that, or rather, there is a significant chance that this resolution is going to be improved. With that open-ended question, I would like to summarize the talk. We demonstrated how thermal channels can be exploited to circumvent strong isolation guarantees provided by spatial and temporal resource partitioning schemes. We raise two key questions here. One, is there an upper bound, or what it is, is there an upper bound on the limits to how much one can achieve isolation in modern multi-core systems? The other question which we would like to raise is that given this increasing trend towards thermally aware computing or energy efficient computing, is there a sweet spot, or is there a compromise so basically we highlight the tension between designing a thermally aware energy efficient system and the security guarantees that can be provided here. With this, I open the floor for discussion. Thank you.
Hi, I'm Mordechai from the Ben-Gurion University. I'd like to ask, and continue to our research about bridging the area between two computers or the thermal manipulation. How do you differentiate between thermal change caused from the external sources, like from people inside the room or air conditioning, in between thermal change that came internally from the computer?
The thermal changes due to external factors, like as humans around the room, will not affect our system.
Okay.
But yes, I agree that the noise generated by applications that are probably executing in different other cores could affect. So the goal of this work was to kind of determine how the best case scenario for an attacker, given such an isolation, how much can an attacker actually gain. I wouldn't say that this is the best that the attacker can gain. Probably tomorrow there will be another research which says, oh, maybe there's some more it can gain. So we try to push the limits and try to isolate everything and see how much an attacker can gain from such a covert channel.
Thank you.
Regarding the temporal partitioning, you said that there was a long latency drop-off time, but what if instead you had the underlying operating system drive the transmitter at a very high rate and heat it up? The rise time is very short, and so you could arrange a scheduler where you had object reuse, basically, and it would always heat up the processor, and then surrounding process, the next process would just always see that it was hot.
Yeah, the problem here is that you should do this heating up randomly. If you don't do it randomly, then there is chances that you can simply average out this effect of constant heating and still extract some data from the temporal scheme. So it still remains to be seen as to how you can potentially lower the data rate of the system. We probably cannot simply avoid it completely, but definitely there are options where you can drop the data rate. But the important thing is you should not reheat it constantly, because that can be easily removed from post-processing.
And I was also going to remark that some people might say, I don't care about object reuse, and they could just see all this variation, and others might turn this on to mitigate a little bit. Scheduler could handle that.
Yeah, potentially scheduler can also handle that, yeah.
So some modern big server farms now use like liquid cooling and things like that. Did you see what the effect?
There are actually, when I was doing my master's, I worked on 3D cooling architectures, and yes, I understand, but these we haven't looked at it because not here. I'm not sure whether we could get access to one such system, and I will be more than happy to experiment with a real system that does 3D cooling or liquid cooling within the cores. Because the problem here is that liquid cooling around the chassis is not sufficient here. You need to go into the system, so you probably need some kind of a 3D architecture cooling within the silicon.
Right.
And I'm not very sure whether there is anything that is readily available with such an architecture.
Thank
Thank you.